Hello class. So this video, we're going to continue in section 3.7. Right? In the previous video, we explained what model we're going to be working with, or what system. We're going to be working with a spring mass system where you attach a spring to a rigid surface, you attach a weight to that spring, and then you give it a pull or a push, right? So you either contract or stretch the spring, and then you let go. And then you look at the position of that weight, which I'm just denoting by the position of this particle here in black, how that moves as time goes by. And again, as I mentioned in the previous video, if you think of plotting that motion of that particle as time goes by, it kind of has this oscillating motion. The same way as the picture of the guitar string gave us an oscillating motion. So what's our goal for this video? Find a differential equation whose solutions x of t, again remember x is the dependent variable, t is the independent variable. So these solutions x of t give us the position of this particle as a function of time. Okay. So in order to actually find the differential equation, it's basically going to be the same thing as what we did in the falling rock example. Right? So first, we need to talk about Hooke's law. So if you remember, this model that we're looking at involves simple harmonic motion rather than more general periodic motion. Why? Because we're assuming that this spring, string, or whatever medium it is that you're working with has a restoration force. Whenever you stretch it or compress it past or below its equilibrium state, it has a force that wants it to go back, right? So that was picture one, right? In picture two, we attached the weight. The weight pulled the string down, and the restoration force going in the opposite direction wanted to pull the string back to its original state, which was the state in picture one, right? And when those forces balanced out, that's when we got our equilibrium position, right? in picture two, when the weight stopped stretching the string. Okay. So Hooke's law, under some assumptions, actually tells us what this restoration force is, right? So what does Hooke's law say? Hooke's law says that the restoration force is proportional to whatever distance we've stretched the spring. So for example, if we've elongated the spring s units past equilibrium, then what would be the restoration force? Well, it'll be proportional to that. And as you know, proportional just means a constant multiple, right? So in this case, if we've extended the spring or stretched it s units past its equilibrium position, the force would be equal to k times s, right? Where k is some constant that we don't know what it is, but it's a proportionality constant. Now, in the literature, sometimes this k here is what is called the spring constant, right? Or the spring stiffness, right? So this k here basically governs the stiffness of the spring. The larger k is, the larger the restoration force is, and you can think of it in terms of stiffness as the more stiff the spring is, right? Meaning that there won't be as many oscillations, right? So larger k is, the fewer oscillations you're going to have because the string is very stiff, right? So when you pull on the weight and let go, it's fast going to go back to its original state, if it does go back to equilibrium, or very fastly, the oscillations are going to get smaller because the string is very stiff. So again, this is determined by how large this constant k is. So let's go back to our picture. And again, we're trying to model, or we're starting our model, and I mentioned this, that t equals 0 is when we let go. So when we let go in picture 3. So how much have we stretched the spring when we're in picture 3, when we let go? Well, we stretched the spring, first of all, s units past its original equilibrium state of just the spring itself, and then we stretched it, and then once we added the weight, and then we were at equilibrium state, right, of the spring mass system, we stretched an extra x units. Right. So we pulled in an extra x units. So total, we've stretched the spring a total of s plus x units. And again, in this case, it's meters. So what is that telling us in terms of Hooke's law? Right. So by Hooke's law, the restoration force of the spring, when you pull on the mass an extra x units, and again, remember we already pulled in it s units by the weight, pulling on itself on the spring. Then what's the restoration force? Well, it's going to be proportional to the distance it's been elongated. So let's say F1 is the restoration force of the spring, which is equal to, so we stretched it s plus x units past the equilibrium of the spring, not of the weight and mass system, just of the spring. So that gives us a total of x plus s units. And again, whatever force this restoration force is proportional to how long the spring has been elongated. So let's just multiply it by k. So we don't know what k is, but we know that given our setup in picture 3, our restoration force is going to be, sorry, I keep going to that slide for some reason. Restoration force is going to be proportional to x plus s, the total distance that the spring has been elongated. Now here, let me make a note so it's clear. I mentioned it a couple of times, but let me make it clear that here we're assuming t equals 0 is picture 3 when we let go of the spring. Just to make it clear, and you can have it in your notes. So because I'm saying it, but I'm not writing it, so I'm going to write it so you know it's clear. Okay, so that's one force that is going to be acting on our object, right? Once we let go. What other force is acting on this spring mass system? Well, there's another force we know about, right? We know there's the force of gravity from the original one. That force is still acting on the spring. So let's call that force F2. Right, so we have F1, the restoration force, and we have F2, the weight. The weight is always the same, right? It's just the mass times the acceleration due to gravity. So I'm going to label F2 to be the weight, which is the mass of the object times the acceleration due to gravity, which I'm just going to call A, where A is equal to where A is the acceleration due to gravity. Oops. Now, those are the two forces that we know for sure are acting on this spring mass system. Now, we're actually going to assume that these, for the start, we're going to make it more general later, but for now, we're going to assume that these are the only forces acting on the object, on the spring mass system. Right? That's only the restoration force trying to go back to the equilibrium state, and the weight of the mass or the object that we put on the spring. Right? And those are the assumptions we're going to put here. Right? So there's no retarding forces. And usually that's the same as saying no damping. So you'll see it in the literature either way. So what are damping forces? So damping forces would be any force that would make our spring mass system lose energy. Right? So again, think about what happens when we let go of this weight in picture 3. This weight is going to start oscillating up and down, up and down. Now, if energy is being lost in that motion, right? Maybe in terms of friction, right? So that's one way that energy can be lost. Well, if energy is lost, those oscillations are going to get smaller and smaller until we're back to equilibrium state, right? Because all of the energy that has, or you can think of it as potential energy, because we've pulled on the object so there's some potential energy saved there. If the energy can escape, that energy eventually leaves the system and it goes back to equilibrium state. Right. So, and again, one way in which energy can be lost is through friction. There are other ways, but that's the most obvious one to see. So for right now, we're going to assume that there are no retarding forces, no damping, meaning that no energy is lost. It's the same as saying no energy is lost in the system, at least due to friction and stuff like that. So no energy lost. Okay. Another thing we're going to assume is that there is free vibration / oscillation. So what does this mean? This assumption means that when we let go of the spring, the oscillations are entirely dependent on the restoration force of the spring and the weight of the object. So what could be the opposite? An opposite thing would be, what if we attached a robot hand to this weight that was forcing oscillations on the system, right? So maybe when I let go, there's a hand attached, or think of me not even just letting go, but me, myself, or a robot hand, if you want to think of it that way, forcing the oscillations on the object, right? So that wouldn't be free vibration because I'm forcing the oscillations, right? I want the oscillations to be completely determined by just the restoration force of the spring and the weight of the object. So that's what free vibration means, or free oscillation. There's no force, there's no other force forcing oscillations on the object other than the restoration force and the weight of the object. Okay? So those are the two main assumptions that we're going to use just to derive our first model. Once we have our first simpler model, when we only have two forces acting on the object, you're going to see how easy it is to add retarding forces or damping, for example, energy loss through friction, and how, or air resistance, for example, and how easy it is to also add the fact that we're forcing vibrations of a certain kind on the system. Right? But we're going to do that later. Again, these are the assumptions. So here, let me write that this means that the weight is completely determined, that the oscillations are completely determined by restoration and weight. Okay, so it's the simplest system we can think of. So restoration force of the spring and weight of the object. Okay. So we have two forces, and this one, let me just label F. So this was just from Hooke's law. So I wrote the forces here. We have a force F1, a restoration force, which we know is K times X plus S. And we have a second force F2, which we know is mass times acceleration. Now, by Newton's second law of motion, right? So the same thing we did in the falling rock example, the total forces acting on the objects are on the spring mass system is just the sum of the forces, right? So the total force, which I'm just going to write F total, acting on the object is going to be the sum of the forces acting on the object. And again, since we're assuming that there's no damping, so no energy is lost, we're also assuming that there's free vibrations, right? So we're not forcing any sort of oscillations on the spring and mass system. These are the only forces we have. Okay. Now, there are signs to these forces, right? Because remember that in this setup, the way I set it up, and you're free to do it a different way if you're coming up with this model yourself, but in this particular model, forces going downward are positive and forces going upward are negative. So we know that the restoration force is going upward because it's going opposite to weight, which is going downward, right? So weight is going to be a positive force and restoration is going to be a negative force. So our restoration is going to be negative. Right? There's going to be negative K, and then the elongation, right, which was X plus S, plus the weight, which is acceleration due to gravity, times the mass. So I'm just going to write M for mass and 9.8 for meters per second squared. Okay. Now, we also know, and actually I think this was just the total sum of forces. I think that Newton's second law is actually the fact that the force equals mass times acceleration. So yeah, I'm sorry, I did that backwards. So this is just a total force on an object is the sum of the forces. Newton's second law tells us that this total force is also equal to, so on one hand, we know it's equal to the sum of the forces acting on the object. And now notice here that I leave K as just an arbitrary constant, right? So I don't want to give a sign to K because whatever sign K has to have is going to come from the model itself. Okay, so there's no reason for me to give a sign to K. K for us is just a proportionality constant or stiffness constant, right? So by Newton's second law, this is equal to mass times acceleration. Mass, we know, is mass. What's the acceleration? Well, we know that the acceleration of the object, if its position is x of t, which we're assuming, right? We're looking for functions x of t that are position, then acceleration is the second derivative. Right? So it's going to be x, let me write it in the long notation. So dx dt squared. So the second derivative of x with respect to time. And again, this is coming directly from Newton's second law of motion and the fact that total force is the sum of the forces acting on the object. Now let me label some things here just so you have them all in one place. Here, I'm going to do it in black actually. So M is mass, F1 is restoration force. F2 is weight. And then, of course, 9.8 just comes from acceleration due to gravity. 9.8 comes from acceleration due to gravity. Right. So this is the setup we have as of now. So let's simplify a little bit. I'm going to get rid of this f sub t in the middle. I'm just going to write m times the second derivative of x with respect to time. Oops. And I should label what x is. So let me do that after I write this equation. So I'm equal to negative k x plus s plus 9.8 m. So let me write here that x of t is the position of the object at time t. When I say the position of the object, you can think of it as the position of this particle that's giving us a position of the object. And t is going to be greater than or equal to 0. Again, t equals 0 is when we let go, right, in picture 3. And anything greater than that is giving you the position when this weight is actually moving. Okay. Now, this is already a differential equation, right? Because we have the derivative, or x double prime on one side, and then x on the other side, and then some constants. However, I can simplify this even more. How am I going to do this? Let me expand some things. So let me again write this. Okay, so now that we know that the variable is t, I'm just going to write x double prime equals, let me expand this, negative kx minus ks plus 9.8 meters. M, sorry, for mass, not meters. Let me draw those k's again. They look kind of weird. So k, that's better. That's better. Now, can you see here what we can simplify immediately? Well, let me give you a hint. Let me underline minus ks plus 9.8 m. We actually know what that is equal to. Why? Well, let's look at picture 2 here. We know that when we're in equilibrium state, and again, equilibrium state is when we attach the weight, right, and the weight stretches the spring, and then it stops, right? That's the equilibrium state. Remember that happens exactly when the restoration force of the spring equals the weight of the object. Now, remember that to get to diagram 2, we stretch the original spring as units. So what is the restoration force in picture 2? Well, it's S times K, right? Because it's proportional, by Hooke's law, it's proportional to however much we stretch the spring, right? We stretch the spring as units, so the restoration force is S times K, and since it's going upward, it's negative SK. We know, since we're at equilibrium in diagram 2, that has to be equal to the weight of the object. What's the weight of the object? It's 9.8 times m. So what do we have? Negative or positive. So the force is negative, but the quantity of the forces are the same, right? So S times K, the absolute value or the magnitude of the force going upward, is equal to 9.8 times m, which is the magnitude of the force going downward. So if we apply that to this, what does it mean? Well, what we're saying is, so let me do it here from diagram 1 and 2. We know that the original restoration force to get to diagram 2, the magnitude of that is equal to the magnitude of the weight. Absolute values make things positive. So in other words, KS equals 9.8 M. And again, that comes from diagram 2. The fact that we're at equilibrium, that means that the restoration force going from diagram 1 to diagram 2 has to be equal to the weight in magnitude, right? Those forces have to have the same magnitude. Well, if Ks equals 9.8 M, and we have negative Ks plus 9.8 M, well, that's 0, right? Negative 9.8 plus 9.8, sorry, negative 9.8 M plus 9.8 M is 0. Right, so this actually simplifies even more to M times X double prime equals negative Kx. Now that I notice, I didn't label K. So K is going to be important because when I show you the animation that I'm going to show you, I want you to know that K, as I mentioned before, the larger K is, the more stiff the spring is. So the oscillations are going to be smaller. So let me, K is the stiffness constant. Let's call it like that. Right, so it's a proportionality constant from Hooke's law, which gives you the stiffness of the spring. Okay. Now, one last thing before so one more simplification. Since the weight has mass, right? The mass is not equal to 0. We can divide by M on both sides. So we're just simply going to write this as negative K over M X. And this is our ODE that models this particular setup. So X double prime equal negative K over M X models so this is doing acceleration, right? But this gives us the position when we find solutions, the position of the weight at time t greater than or equal to 0. And we've derived this differential equation. So again, it's a lot of work because we had to explain how all of these forces interacted, right, in the original pictures. But once you see how the picture works and you think about what's going on, then the setup of the differential equation, again, is all coming from Newton's second law and the fact that the total force is equal to the sum of the forces. Okay. So this is the model. Now, before I finish this video, because I don't want to, it's already a little bit long, but there wasn't really any natural place to stop. We can also add some initial conditions. For example, let's say we want to add an initial condition here. Let's say that we pulled the spring down, let's call it X naught units, right? And we let go, right? Then the position of the spring at time 0 would be X naught units, because again, remember, position underneath equilibrium is positive. Position above equilibrium is negative, right? So for this particular example, we could say that X of 0 is X naught, meaning that we pulled the string down, or the spring mass, let me just say the weight, down X naught units past equilibrium. So I'm saying down, so it's going to be a positive number. If I say push it up, it's going to be negative. And then for initial velocity, similarly to how we did it in the rock case, if we just let go, the initial velocity is 0. However, if when we let go, instead of just letting go, we push it up or pull it down with some sort of initial velocity, then the initial velocity will not be 0. But in general, we would have some initial velocity at time equals 0. What should I call this? I might change this notation later. For now, let me just call it x1. Again, I might change this notation later. I might call it something else, but basically this is initial velocity. Initial velocity which again, what it means is that you just let go or you give it a pull or push. Right, so that's where the initial velocity comes from. If you just let go, the initial velocity is 0. Right? And this is our model. Actually, let me square it in a different color, including the initial conditions. We don't know what they are right now because I didn't give you specific ones, but this is the setup. Of course, with the assumptions that there is no damping. So last thing I write, I promise, on this video. So under the assumptions that we have, well, there's actually 3. First, that there's a restoration force. Remember, that was equivalent to saying that there's simple harmonic motion. So there is a restoration force. There is no damping, right? So there's no energy loss. And there's free vibrations or oscillations, meaning that we're not forcing any sort of oscillations on this system. Everything's happening on its own. Okay. So these are the 3 assumptions. We get this model.